Okay, thank you very much. So I would like to thank the organizers for giving me the opportunity to speak here, and also to make a disclaimer that I'm here privately. So I'm not really representing BNL for some political reasons. Okay, so as in contrast to previous talks, I'm going to talk about direct space. I'm not going to give you some enlightening.
You are recorded. It's okay or not?
That's okay. I mean, I will be long gone by the time the recording is published. So anyways, and so this is sort of a technique development talk rather than some kind of highlighting science on a specific material. Let me first acknowledge the source of funding, and specifically to thank the people from MFX, that's molecular femtosecond crystallography beamline at LCLS at SLAC, where this work has been done, as well as colleagues at APS that helped us with some kind of characterization measurements. Okay, so this is a teamwork, so there is a large team. This experiment, it turns out it's actually quite complicated, and most of the work has been done by the postdoc Jack Griffiths. Without the colleagues from LCLS, this would not have happened. Okay, so the goal that we were after is to develop a tool for a local structural characterization, so length scale sensitive atomic GPS in the ultrafast context. So you have an equilibrium state A, you actually zing it with a laser pulse, and the system goes to some kind of, let's say, metastable state C. And so the question is, what happens in the middle? So that's what we would like to actually explore. So development of materials with specialized and highly efficient properties increasingly relies on complex local structures that stray from the ideal of a perfect crystal. In other words, basically local heterogeneities in electronic systems. On the other hand, the advancements in electronic technology drive the need for materials that can be switched between distinct states, electrical, magnetic, structural. So a key example that we are actually focusing on is the metal insulated transition. Why ultrafast? Well, this was actually presented somewhere else, so it's for a slightly different audience. 1 picosecond is the time scale for electron-phonon coupling, and also femto and picoseconds are natural time scales for the electronic, for the phase transitions. Okay, so another aspect is that oxide electronics utilizes ultrafast metal insulated transitions. So there is a number of materials, there is a number of switching mechanisms, and then there is a number of properties. But ultimately you have basically two states that you want to switch back and forth from. So here is an example of that. So this is ultrafast resistive switching in a famous 1T tantalum disulfide. This is work done by the group from Ljubljana. And so you can apply a pulse, you can actually write, so change the resistivity. You can apply another pulse and you can erase the state. So that's sort of the idea. And then in this particular system, it's a very famous charge density wave material. You have a cascade of first order phase transitions from a high temperature metallic to a low temperature commensurate charge density wave and everything in between. So this will become relevant just for a question that I want to pose. Okay. There is also switching that you can achieve in vanadium dioxide based devices, and you can utilize various channels to control the properties to your liking. Okay. And then to characterize disorder in this type of systems, it has been recently reported, actually, the ultrafast disordering of vanadium dimers in another famous system, vanadium dioxide. And so it turns out this was a study that was done on a single crystal that you actually have to focus on diffuse scattering features upon application of your pump. So what they were specifically looking for is whether the nature of this transition is displacive, in which case the diffuse channel is inert, or order disorder, in which case you actually, apart from Bragg pattern switching, let's say, you also have a diffuse signal that pops up. And so that's what they sort of saw. Now, the problem with this is that, number one, you're actually assessing information over a very limited Q-space range. And number two is it's a bit shaky how to interpret the data, actually. What does it mean, what you see? So simulated vanadium dioxide response was done in this work based on first principles DFT calculations. And as I said, diffuse scattering is generally difficult to interpret beyond this simple-minded order disorder scenario. Okay, so that being said, let me just get back to 1T tantalum disulfide. So there was this switching that was reported in this system at low temperature, and as you do your pump pulse, you actually make the system more metallic, and this state is long-lived. It actually can live for weeks, according to Dragan. However, you can actually destroy that state, that hidden state, which is not observed in equilibrium, by heating up above 50 Kelvin. You can also do the switching at higher temperatures, but then that metastable, that hidden state is no longer metastable. It actually very quickly decays. And so one of the questions that one might ask is, why is quote-unquote 50 Kelvin special in this system? And what is the symmetry of this hidden state? Is there a difference? Is there a difference in the states that you are pumping on, or is there a difference in the states that you are actually ending up in? And so this is the ultimate, from my standpoint, perspective, the method that we have developed that we would like to look at next. But what is the method? Well, in equilibrium, advanced Fourier maps have been instrumental in characterizing disorder on a nanoscale. And back 35, 40 years ago, in the time of cuprates, powder 1D PDF mapping has arisen from glass and liquid community and applied to crystals. And in that, you do have actually a conventional diffraction pattern that extends, which is important, to very high Q, which actually determines the resolution in real space. And you also have a diffuse scattering channel, and so you can treat those two signals simultaneously on equal footing. And so you end up with a basically function in direct space, which has intensities that correspond to interatomic distances. And you can interrogate your signal over different length scales to determine actually how local and the average structure connect. More recently, you also have a single crystal version of this, which is essentially called 3D peer distribution function method, in which you actually collect data, or you collect maps over very broad Q ranges, and then due to the fact that those signals are actually of different type, you can punch out, brag, and actually propagate only diffuse scattering signal, which you then 3D Fourier transform, and you end up with a map, which is called 3D differential PDF, which gives you an information of how your atoms are actually deviating from the crystallographic structure. So what we wanted to do is to bring this logic and this methodology into the ultrafast regime, to be able to actually move forward the nanoscale characterization. So in equilibrium, these are just few examples to see, to demonstrate you how it works. We actually looked at tantalum disulfide that I mentioned previously, and what one needs to know about the 1T polymorph is that that's a metastable state. So you start with the tantalum disulfide, you quench it, and so long as you stay below certain temperature, you are in 1T state. If you heat it up, you're going to violate metastability, and you're going to end up in some other polymorph irreversibly, unless you reset it by quenching again. Okay, so in that system, at lower temperatures, but in the metallic state, where the system is still 1T, we have observed actually polaronic signatures that are actually very short-ranged. which brought a new scenario for this cascade of phase transitions to actually be a polaron crystallization into a Wigner crystal-like state. So that could be the entire different talk, but that's something that you can get from this 1D PDF. The other thing is if you get bold and you actually heat it up above this violation temperature, you will convert the system from 1T type environment, which is actually octahedral coordination of tantalum, to 1T and plus 1H mixture, 1H being trigonal prismatic. And as it turns out, in all the polymorphs that could appear, you will have 50-50 mixture. So it's either 4HB or it's 6R. And so interestingly enough, if you follow PDF signal across this heating, you do see that the polaronic signal drops by 50%. So this suggests that the actual precursor polaronic state is associated with 1T type layers. Okay, so that's sort of off the topic, but it actually gives you an idea of what types of stuff you can study in equilibrium. The system that we actually used for our ultrafast PDF development is copper iridium 2 sulfur 4. And that is actually the one that satisfied several needs from technical standpoint. One is obviously that it has a metal insulated transition. So it has a metal insulated transition on cooling, where your system goes to high temperature spinel cubic structure to triclinic dimerized, spin singlet dimerized state. And that has actually a very strong response in the structure. So this is a PDF, actually a neutron PDF, published some 25 years ago. The distortion is half an angstrom large. So the short dimer bond appears as a new peak here, which is very well resolved from the principal iridium peak in the undistorted matter. This is this big guy here. Okay, so the transition in equilibrium is proposed to be orbital iridium pulse transition. So we have studied this system with PDF some time ago, and so here you see a stash of PDFs as a function of temperature as you go from low temperature dimerized to high temperature cubic regime. And so if you take a look at this figure alone, you don't see anything special going on. Basically, you see a transformation taking place on all the length scales. So then you can apply a crystallographic model, that's the top figure, at 500 Kelvin, so the latest data set that we had. And the fit is actually really good, except that there is actually a discrepancy underneath this second peak, which is iridium-iridium near neighbor distance on a pyrochlore sublattice in this system. And that is actually, that was the discovery of this precursor state that actually lives for as high as we actually measured. That was like 800 Kelvin temperature. And this state is distinct from the from the spin singlet dimer state in that the distortion is an order of magnitude smaller. So the actual dimer peak, which is shown here, disappears upon heating. Okay. That state is electronically different from the dimer state, but I'm not going to go into that. Another interesting aspect of this system is that you can actually melt the long-range dimer order in the monoclinic, in the triclinic actually structure by applying any kind of radiation, X-ray, ultraviolet, or electron beam. And so then the system goes not to cubic, it goes to actually a tetragonal average symmetry. And you have these actually diffuse scattering wings that develop at low temperature. You can then reset by basically annealing the system. As it turns out, we applied PDF methodology there as well. And so these are 4 different diffraction patterns from an image plate that correspond to different exposure. And I mean, the detail is that one multiplet of Bragg peaks, because this is actually a low resolution measurement, disappears. It has actually this kind of time dependence. The time scale here is in seconds. So you can melt the long range order, but if you take a look at the PDF originating from the same data, you do see that the dimers are staying put. So So you're not actually destroying the dimers, you are essentially just destroying the long-range order. Okay, so relatively recently again, this system was looked at by the group in Ljubljana, and they studied actually ultrafast reflectivity, and they claimed that there is a new transient state that actually occurs because and the reflectivity decreases initially and then recovers over sub-picosecond time scale and tens of pico time scales respectively. And this unidentified transient state appears to be weakly conducting. So this was done actually at low temperature, which is suggestive of this strong dimerization being removed. And so we wanted to sort of test what is happening with this system in ultra-fast regime from the local structural perspective. Another reason, probably I mentioned it, I kind of forgot, so I'm going to say again, why we were after this system is because iridium is a very heavy atom, and it actually has very strong scattering properties. Because what we are going to do now is we are going to actually do a pump probe. I managed to, okay. To do a pump probe measurement where the pump is a laser and the probe is an X-ray. And so that's, we were not actually sure what to expect, and you know how it works at those large-scale facilities. You only get one chance to try something that nobody tried before and prove that it works. You cannot prove that it works if you haven't done it before, right? So it's kind of, it was kind of highly political. And so we wanted to go for a slam dunk system, and that was copper iridium 2 sulfur 4. Okay, so before going there, we have done an experiment at APS in equilibrium, where we actually tested whether specially prepared submicronized sample still has a phase transition. So that was one aspect of the test, and it does. So you sort of see here comparison of above and below the temperature-driven phase transition PDF profile, and you see clearly that there is a dimer peak. Now, this is a very high real space resolution measurement in that we actually had access to 30 inverse angstroms Q. Now that we have that data, we can degrade it to the expected Q range of the LCLS measurement that we are just about to do, and see if we can still see actually this phase, the temperature-driven phase transition, and the answer is yes. We could see it. So there is, in this kind of extra resolution mode, there is this W kind of signature that signifies that the dimers are being removed. Okay. So these are the details of our LCLS measurements. I'm not going to go through them. I'm just going to say that we covered a regime between -20 to 100 picoseconds delay time with a resolution of 1 picosecond. And unfortunately, we did not get any data in sub-picosecond regime, which turns out to be, on some level, critical. But there is no limiting factor to not be able to do that. So here are the PDFs that are color-coded and plotted on top of each other. It's not really very important that you can actually see specific profiles, but what is important is that stuff is happening as a function of delay time. And so then, okay, we wanted to look at underneath the iridium peak, whether there is this W signature of dimer removal. So here, gray profiles are difference between negative time delay data and a selected negative time delay reference. And then the colored profiles are those that are actually coming from positive time delay PDFs. And so you do see clearly that once you cross 0 time, you do see this W feature, meaning the dimers are being removed by the laser pump. So this is the same difference curve, stack of the same difference curves over a much broader R range. And so one observation that one can make here is that initially, like once you pass 0, but immediately after you pass 0, the scale of those difference curves on all length scales is the same. However, if you let the delay time lapse, you start seeing that higher R differentials start gaining intensity, whereas the low R region does not change. That is actually strongly suggesting that there is a time evolution of the atomic structure on different length scales, and that evolution is different. So to quantify that, we calculated root mean square of the intensity signal of this differential over these three regions. So you get a single number per profile, let's say. And so what you see is that for this short-range structure, you do just observe a jump. There is actually no structure to it because we did not have data in the sub-picosecond regime. So anything that has happened to the local structure happened in basically femtosecond regime, which agrees with, for example, vanadium dioxide, where you actually melt the dimer order on the time scale of 100 femtoseconds, I think. Whereas, if you look at those blue and red boxes that correspond to the longer time length scales, you do see a jump that follows by a much slower relaxation, which is actually of the order of 40 picoseconds time constant. So the longer length scale structure evolves further, whereas the local structure does not. Okay? And then we actually compared this differential, that is something that I was supposed to mention before, that was obtained in this pump probe experiment, that's the black curve, with the signal that you obtain if you drive the transition by temperature. And it turns out you had to scale the temperature-driven response by basically 0.3 to get the same scale, which suggests that in our sample, there is about 30% of dimers being removed. There's multiple reasons that could cause this. One is obviously that our grains are large and that actually laser penetration depth is small and that we see actually just a fraction of dimers just because we access only a fraction of our sample. However, 30% is way too large. And so the other explanation could be that actually there is another mechanism, such as non-thermal electrons that are carrying energy that actually destroy dimers further. Okay. The other thing that you can do ultimately is that you can actually do structural refinements on such a data. So we have tried this. So we fit a cubic model, tetragonal model, orthorhombic model, and another tetragonal model. And all of them are actually fitting the data, except that cubic model never works. And the cubic model is the model that actually describes the equilibrium high temperature metallic regime. So that's one thing. The other thing is, it seems, according to this analysis, that basically the symmetry for the short delay times is actually lower than the symmetry for the higher delay times. And that change happens over the time scale of about 12 picoseconds. Another important aspect of PDF analysis is basically focusing on atomic displacement parameters, because they, in case of thermal motion, give you temporal variance, but in case of disorder, they actually capture spatial variance, and that's what we utilized. And so this is what you get. So if you focus on one of those models, specifically, I think it was a tetragonal model, it does not really matter, and you do a sliding window refinement. So you select the window size, and you basically define your data over different ranges, and you extract parameters that you obtain from such fits. It turns out that the only parameter that really changes in some meaningful way is the atomic displacement parameter of iridium. And so this is the map of the iridium displacement parameter as a function of, on x-axis, refinement range, and on y-axis, pump probe delay time. And so what you do see is that locally, meaning for the short length scales, you do not have actually enhanced value of this ADP. It's of the order of 6 times 10 to the minus 3 angstrom squared, which is what you expect at the 150 Kelvin temperature in equilibrium. However, at the longer length scales, you do see that this parameter gets enhanced by 3.5 times. for short delay times. And then that this actually relaxes as you go towards longer delay times. So that's reflected in this couple of curves, depending on the range. And you can extract from there a time constant of the order of 40 picoseconds. So this is suggestive of actually there being a disorder in the system initially as it gets perturbed by the pump, which relaxes towards a long-range ordered structure as the time delay proceeds. Okay, so this is the rationale behind that. So we basically observe there is probably three time scales, but we observe two because we have missed the show in sub-picosecond regime. One is 12 picoseconds. That is essentially the evolution of lattice parameters of various models. They all suggest the same length scale. So that's related to there being different local configurations. So you could have basically different configurations pointing in different directions, and that kind of evolves as a function of time. And then it sort of, I wouldn't call it, but let's say locks in after 12, on a 12 picosecond time scale. So you get your sort of space group within this time regime. But nothing actually limits disorder still being present in that and actually evolving over a longer time scale. That's exactly what we observe. So any proportion of configurations can be actually either ordered or disordered, which suggests that the ordering time scale is independent on the one that is suggested by the lattice parameters. Okay, so that's all I had to say. So here's the summary. So optical pumping removes strong dimers in this test system in a sub-picosecond regime, which we haven't probed. System does not return to the high temperature metallic cubic phase. The removal of dimers is initially spatially disordered. So basically different regions do not talk to each other initially. But order reestablishes over the 40 picosecond time scale. The atomic displacement parameter mapping leverages the PDF strength and actually tracks disorder in space and time. So this sort of gives you the vehicle to extract this type of information. The most important part is, as I said, not related to this specific material, and it is that ultrafast PDF is a feasible tool at current exfil facilities. However, under the present setup limitations, it needs favorable sample, both in terms of preparation and in terms of scattering properties, and it needs reference synchrotron data. That's a detail that I cannot go into here. So there is actually a huge enthusiasm in the PDF community, particularly in Europe, in developing this method. And so I think that we are onto something very interesting. So we can then apply basically this methodology to other systems, such as those that I mentioned, vanadium dioxide, tantalum disulfide, and so on. And basically the pool is large. So with that, I thank you for your attention, and I hope it wasn't too terrible.